So we've seen that permutations take into account the order of the objects. A combination is a grouping of objects in which the order doesn't matter. The first thing you have to be able to do is identify the two situations. So in the next example, which again is not in your book, suppose we were selecting 6 free songs to download from a list of 100 choices. Would this be a permutation or a combination? The essential question is, does the order in which the songs are downloaded matter? So if I download Dust in the Wind and then Candle in the Wind, sticking with the theme, and then let's say plus 4 others, would I want to count that as a different arrangement than me getting 4 others plus the Dust in the Wind and the Candle in the Wind? And the answer is there's no difference between these two because I end up with the same 6 songs and the order in which I downloaded them is not relevant. So that would make this first situation a combination. Determining the number of possible top 3 finishers for a race with 100 people, is the order important in a race? And the answer is, of course, yes, because you will have a first place, a second place, and a third place finisher. And it definitely seems like a different arrangement if I come in first and, somebody else is second, somebody else is third, versus me coming in third. Those are two different race results, and I would need to count each of those. In other words, the order is important, and therefore this would be a permutation. So just like with permutations, we have a notation for that. For example, in this case, the race had 100 people, capital P for permutation, and I'm choosing top 3 finishers. So that would be 100p3. Going back to example 1, the combination, we do use big capital C for combination. We put 100 on the left, the total number of choices, and then the number we are selecting, which in this case was 6, on the right. Now, because combination, the order does not matter, there tends to be a lot fewer ways to do this than there are permutations. Here's the formula that helps us calculate it. The number of combinations of R objects selected from a group of N objects without regard to the order, meaning order doesn't matter, is given by this. Now this looks very much like the NPR formula, which if you recall was n factorial over n minus r factorial. The only difference between the two is the addition of this r factorial on the bottom. And again, because it's dividing the numerator, it's reducing the number of possible ways that this can occur. Once again, you're going to be able to use your calculator here to calculate these values. You will not typically need to resort to the formula. But you should be familiar with the fact that there is a formula behind those values you're getting from your calculator. In example 5, we have a state's Department of Transportation planning to develop a new section of interstate highway, and they get 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of companies can be selected? So you'll notice that the word combination appears. How many different ways is telling us we're going to need our counting principle here. It should be clear that the order that the bids are chosen doesn't matter. Whatever 4 companies I pick, there's nothing special about being the first company to be chosen versus being the 4th. So in order to calculate what this would be, I would do 16 as my total number of companies. It's a combination, and I want to choose 4. Now, according to the formula, that's the same as n being 16, r being 4. I substitute into the formula and I get 16 factorial over 16 minus 4 factorial, 4 factorial. And these are being multiplied. This is the same as 16 factorial divided by 12 factorial times 4 factorial. And again, you can either type this original 16C4 into the calculator, or you could type in this side. You should get the same thing either way, but bear in mind, again, you're going to want parentheses around that denominator. So if I calculate what 16C4 is, I'm going to get a total of 1,820 different combinations. So certainly more than I would want to try to list and count up. You should be able to tell when a situation would require the use of combinations or permutations. So for each of the problems in the next example, the first thing that we need to do is decide which one we're going to use to answer the question, and then part B, solve it appropriately. So question 1 says, how many 3-letter arrangements are there of the letters in the word computer if each letter is only used once? So in other words, if I was making 3-letter arrangements, I might make COM. And would I count that as a different arrangement than MOC? Yeah, I can tell these apart. I can tell that they're different. So therefore, when you're arranging letters, order is important, and that means this is going to be a permutation. Once we know it's a permutation, we're going to count up the total number of letters in the word computer, which is 8. And of those 8 letters, we are being told to use 3 in an arrangement. So we would need to calculate the value of 8p3. There are 336 different arrangements. Number 2, how many different ways are there to arrange the letters of the word alphabet? So it seems like we're doing exactly the same problem as the last one. We're arranging letters, so this is again going to be a permutation. So first of all, we're being asked to arrange using all of these letters, and the way that you would do that would be 8 factorial, because there'd be 8 choices for the first blank, 7 for the next, 6, and so forth, all the way down to 1. However, because we have repetition, we're going to need to divide that out. So we have the letter A, which repeats, and that's it. The rest are unique. So A repeats twice, meaning I need to put a 2 factorial in my denominator. 8 factorial divided by 2 factorial, you can type it into your calculator like this. If you're a fan of simplifying things, you could write out what the factorial is equal to in the numerator and in the denominator. Cancel the things that are equal to 1, and then this is really what you're computing. This is what's left, 8 times 7 times 6 times 5 times 4 times 3. You should get 20,160. How many ways are there to pick a committee of 3 people from a group of 9? Well, there's no indication that any particular person here is special. So if I pick a committee and end up with Bob, Jose, and CJ, is that a different committee than if I have CJ happens to get selected first versus Bob and Jose? These would be the same 2 committees. So in other words, order is not important. If order is not important, this is a combination problem. And if we want to pick 3 people from a group of 9, that would be 9C3 is equal to 84. So there's 84 different committees that could be formed. And our last example, it says, in a store there are 3 kinds of fruit and 4 kinds of vegetables. How many different ways can a person buy 2 fruit and 2 vegetables? Now, what's new in this situation is we're selecting 2 different kinds of objects. We're selecting fruit and we're selecting vegetables. And the counting principle says that we need to calculate each of these individual ways to do things, figure out how many choices we have, and multiply them together. So, when it comes to me picking two fruits and two vegetables, is the order important? Would I consider orange, lemon, carrot, green bean different than lemon, orange, green bean, carrot? And the answer is no. I would end up with the same four groceries. It doesn't matter what order they're chosen in. So, therefore, this is going to be a combination problem. And you want to be careful. If you have multiple kinds of objects, you will want to set up multiple kinds of C's, one for each type of object. So first of all, I'm going to say, okay, my fruit. How many options do I have? There are 3, and I'm supposed to buy 2. So 3C2 would calculate the number of ways I can do that. Then I'm going to set up a C for the vegetables. There's 4 kinds, and I'm looking to choose 2. Counting principle says to get the total number of ways to do 2 separate things, you're going to multiply those together. 3C2 equals 3, and 4C2 equals 6. So there are apparently 18 different ways that I can choose the 2 fruit and 2 vegetables. Now, as long as all the questions say how many, all you need to just do is decide whether it's a permutation, combination, and calculate using the appropriate method. However, when we switch to saying, what is the probability, you may need to use permutations and combinations as part of the process. But because it says what's the probability, I don't want to give an answer like 18 or 2,572. I need to give a fractional answer. So we're going to have to consider separately the numerator and the denominator that's appropriate. From a student advisory board of 17 members, we are choosing 3 to serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve in any of the positions, so there's not like a senior member who would automatically be the chair. What's the probability of randomly selecting the 3 members who will be chosen for the board? So first of all, we need to decide, would this be a permutation or a combination? In this particular case, because this committee has specific positions, these are distinct. And because they are distinct, again, kind of going back to my 3 people from before, choosing Bob for the role of the chair, and then Jose for secretary, and CJ for the webmaster, is definitely a different committee formation than if I change up Jose and Bob, make Jose the chair, Bob the secretary, and keep CJ as the webmaster. So again, order is important here. I'm choosing for specific positions. If I want to calculate the probability of selecting 3 members, and I know that my situation here is a permutation, in the denominator, I always consider the total number of ways that something can be done, the total number of possible outcomes. So I need the total number of ways to select 3 from a group of 17 people. That's going to be my denominator. And to calculate that denominator, we would want to do 17p3, giving my fraction a denominator of 4,080. Now, what's the probability that I randomly select the 3 who end up getting chosen for the board? Well, the 3 who end up getting chosen for the board, there's only going to be one person in each spot. There's going to be one person who's chair, one person who's secretary, and one person who's webmaster. So I would multiply those numbers together, and there's only one way to select the 3 people who did get picked, giving me a numerator of 1, meaning my probability is 1 in 4,080, and as a decimal, that's very small, 0.0002. So said another way, suppose I came up to you and said, hey, my advisory board today has 17 members, and we chose 3 people who to be chair, secretary, and webmaster. Try to guess who ended up in what spot. There's only one right answer out of 4,000 possible choices. In example 7, we're asked to find the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. Does it matter what order the cards are selected in? If I happen to get the 4 of diamonds, then the 3 of diamonds, then the 5 of diamonds, then the ace of diamonds, and then the king of diamonds, would I count that as a different outcome than getting king of diamonds, 3 of diamonds, ace of diamonds, 5 of diamonds, and 4 of diamonds? Is the order important? Are these distinct outcomes? And the answer is no. Having these 5 cards be the ones that I end up with, I am holding the same 5 cards, even if I'm holding them in this order. Therefore, order is not important here. So this would be a problem we would use combinations. So if I want to calculate the probability of selecting 5 cards that are diamonds, I need to know my denominator, again, always has to represent the total ways. So this is the total number of ways to pick 5 cards from 52. In the numerator, I want to know the number of ways to get 5 diamonds in particular. I divide those two, and that becomes my probability. So when I say the number of ways to get 5 diamonds, if I want to get 5 diamonds, I'm not using all 52 cards as my total number of cards, because I want to focus specifically on getting diamonds. How many cards are diamonds? 13 of them. And I want to choose 5. So in my numerator, the outcome that would be a success is of those 13 cards that are diamonds, choosing 5 of them. On the bottom is going to be the number of ways to pick from 52 cards, 5 cards. When you calculate your numerator, you're going to get 1,287. When you calculate the denominator, you're going to get 2,598,960. When you pick up a calculator and divide out these, the probability again is very, very small. It's less than 1%, that I would actually get 5 diamonds. So if you play poker, this is where you can get into all of those probabilities of different events occurring and how rare they are. And of course, that then determines the ranking of the different winning poker hands. Probability, again, can be challenging to students because of this idea of you've got to understand how to determine if something's a permutation and a combination. If the problem says how many ways can I do something, that's easier because you're just going to use the capital P, capital C, maybe use the factorial. But if it says probability, you have to make a fraction. So you have to figure out what you want your numerator to be. And the numerator should always represent the outcome you want to have happen of being successful. And the denominator should represent just all the ways that you might do a particular task.